Okay, recording. Right. So there's on the next page there's an example calculation around ideal transformer. So electrical system requires an input voltage of 120 volts. The input voltage to the site is 14.4 kV. What is the required turns ratio of the transformer to achieve this voltage step down? Yeah. If the secondary current is 500 amps, what's the primary current? And assuming an ideal transform, confirm the conservation of power. So first of all, the turns ratio, and later on we're going to be calling the turns ratio I. Yeah. So we can express it either as N1 over N2, or we can express it as a ratio I. So from this equation, we know that N1 over N2 has got to equal V1 over V2. Yeah. So V1 is 14,400 and V2 is 120. Yeah. So that turns into a ratio of 120 to 1, because 120 goes into 14,400 120 times. All right. So what if we had one, what's down here is if we had one turn on the secondary, we'd need 120 turns on the primary. Or we could say for every turn on the secondary, we'd need 120 turns on the primary. Yeah. Second part, secondary current is 500 amps. What's the primary current? So using the I1 over I2 is equal to N2 over N1, using that version rearranged here. So we brought I2 up and multiply. So equal to 500 over 120, 4.17 amps. Hang on. Oh yeah, because there's N2, I2 is 500 amps, N2 1, from our ratio over 120 N1, 4.17 amps. All right. So for a primary current of 4.17 amps at 14.4 kV, we get a secondary current of 500 amps at 120 volts. Yeah. And the conservation of power, if we multiply V1 by I1, yeah, we get 60,000. And if we multiply V2 by I2, we also get 60,000. Yeah. So this is a 60 kVA transformer. Yeah. Now when we analyze a real transformer, we bring the losses in for the given nominal VA of the primary, we'd end up with slightly less volt amperes out of the secondary because of the losses. And that's what we'll develop over the coming weeks. Yeah. Okay with that, everyone? Yeah. Good.
No,
Go on.
No, I think I'm still quite. I didn't understand. So primary current I1 is given by. If I1 is N2 over N1 times I2, why is it 500 over 120?
Because N2 in the ratio, N2 is 1, Ben.
Oh, right.
Yeah.
Oh, yeah, I see. Yeah.
Yeah.
Right. Okay.
For every one, it doesn't matter if you said there was 10 turns on on the secondary, well then you'd have 10 times 120, which is 1200. You'd still get the same answer, wouldn't you?
Yeah, yeah. Right, go away.
So that is N2, which is 1, times I2, which is 500, divided by 120. All right?
Yeah,
I
fine.
agree. Perhaps at this early stage, perhaps that ought to be clearer. But that's how it works. All right?
Yep.
Yeah? Right. So, an ideal transformer has 1200 turns on the primary and 300 on the secondary. So N1 is 1200, N2 300. Supplied via voltage EG of 400 volts. So V1 is 400 volts. And the load Z is a per resistance of 12 ohms. So ZL equals 12 ohms. Yeah, calculate the voltage secondary E2, the secondary current I2, the primary current I1, and the apparent power in VA delivered to the secondary. So where are we going to start on A? Given the information we've been given.
So if you use a turns ratio, you can, and the voltage supplied, that can give you the secondary voltage by using the
Yeah.
N1 over N2 thing.
Yeah, we can use, we want to find E2. So we can say E2 over E1. And we know N1 and N2 as well. So we can say that's equal to N2 over N1. Yeah?
Yep.
And then you can transform that to V2 is equal to V1 N1, N2, sorry, over N1. Yeah? That is 400 volts times N2, 300 turns, over N1, 1200 turns.
So you got 100.
100 volts. Yep.
Yep.
Secondary current, B, I2, is equal to
We go for the same formula again. So you could use, well, you've been supplied the values for the turns ratio. So if you use the turns ratio against the current and then rearrange that, then that would be, you'd get I1 over I2.
Yeah, but both currents are unknown at the moment.
Oh yeah, they are. I'm being a helmet.
I won't go that far.
So you've got the resistance of the load. Would that give you the, that would give you the current, went it through the secondary side?
Yep, because you know V2 and you know ZL.
Yeah.
So it's just Ohm's law. Yeah, V2 is 100 over 12 equals
3.34. Oh no, 8.34.
yeah.
Be a bit strange.
8 1/3.
Yeah.
Yeah.
Yep.
C, primary current. So you want to know I1. Any ideas?
Yeah, so you must be able to use the I1 over I2
You can now because you know one of the currents, don't you? So you can go over I2
equals N2
is
over
equal
N1.
to N2 over N1. And that's really the right one to choose because you were given both of those values in the question as opposed to using a calculated voltage. Yeah.
Yep.
So that transforms to I1 is I2 times N2 over N1. I2 was 8 1/3 times N2, 300 over N1, 1200.
We've got 2/3 for that.
Are we expecting it to be less or more?
That should be, yeah, it should be less, shouldn't it? Because that's the,
Yeah, that's the primary side of a step down, yeah?
yeah.
Yeah, I got 2.
So I got 2.08.
Yeah, that's what I got too.
Oh, something's not right on my calculator then.
What are you putting in, Robbie? You putting 8.34 or?
No, I put 8 1/3. I'll put a plus in the middle of it, see if that makes any difference. Yeah, it did.
8
Yeah, I just
1/3.
put 8 1/3, and then I put
Yeah.
8 plus 1/3 in brackets, and that gave me 2.083.
Yeah, I always use the fraction thingy.
Yeah, that's what I did. I used the fraction
Yeah.
button, but I think because I just put 8 next to 1/3, that might multiply.
I'll do
it
8
rather
times
than
a
add
third
it.
then.
Yeah.
It will. Yeah. Right, parent power delivered to the load. So we want S2. Remember, S is measured in volt amperes. No? Lewis? Any ideas?
V times I.
Yeah, so it's going to be V2 times I2. V2 was 100, wasn't it?
Mm-hmm.
Times 8 1/3. 833 VA. Yeah.
Yeah.
Okay.
Mm-hmm.
Yep.
All right. Everybody okay with that? Fairly simple.
Yeah.
Ideal transformer calculations. No losses. So you just use the ideal transformer equation. Yeah.
Yep.
You can rest assured you won't be getting one of them in the exam.
Oh, come on, please.
All right.
No.
So, terms ratio for ideal transformer. If finding the terms ratio A simplifies some of the calculations around transformers. Because if we say that A is N1 over N2, yeah, what we can then do is we can rewrite that E1 is A times E2, the transformer ratio times E2. Do you see where that come from? Or not?
Yeah, it's just like the rearranged formula of
Yeah, because if you've got if
Yeah.
we start off with the full formula, E1 over E2 is equal to N1 over N2. Yeah.
Yep.
And we want to find E1, we would bring E2 up and multiply. So we'd say E1 is E2 times N1 over N2. So if we call N1 over N2 A, it equals A times E2.
Yeah.
And the calculations we're going to do later on, they're much simplified by using the ratio A rather than the separated N1 and N2 values.
Yeah.
All right, because A is actually equal to N1 over N2, and is equal to E1 over E2. So you can get that ratio from either the number of turns or the voltages. Yeah. And then you can also write that I1 is equal to I2 over A. Yeah. Do you want to see where that one comes from using the whole equation?
Yeah, go on then. Might as well find
Because
it.
we know that I2 over I1 is equal to, I'm going to do it in terms of I1, 1 minute. So I1 over I2 is equal to N2 over N1. Yeah.
Mm-hmm.
So if we turned N2 over N1 up the other way, we've got to turn A up the other way. So it's equal to 1 over A.
Yeah.
N2 over N1 is equal to 1 over A. Do you understand that? Yeah. So we'd rearrange this equation to I1 is equal to I2 times N2 over N1, which means that's equal to I2 times 1 over A, or it's equal to I2 over A. Yeah? Everyone follow that or not? Have I been too confusing with that?
No, I get that one. Yeah, it's fine.
Yeah. And then, so what we've got then is these, just going to do a new page. We've got these two equations for voltages and currents, where we've said that E1 is equal to I times E2, where therefore E2 is E1 over A. Yep. And we've got I1 is equal to I2 over A, which rearranges to I2 is equal to A I1. And the calculations we're going to be moving to, those four make that much easier. because you got rid of the N1 and N2 separating values. All right?
Yep.
Ben, okay with that?
Yeah, I think so.
Yeah? Yeah. Lewis?
Yeah, I got it.
Warren?
Yeah, it's fine.
Good. So, how are we doing for time? Left time, have we got a bit yet? Right. So, impedance ratio. So, what we're going to do here is look at how the generator, when an impedance is connected to the secondary Z, this impedance here, what impedance does the generator see? What does the generator think it's got connected to it, which will be different to its actual value? Yeah, we connect a generator to a primary, and we call that voltage at the primary terminals E1, and a current flows in the primary coil, and we got a turns ratio I is equal to N1 over N2. We get a secondary current, the secondary voltage across the terminals, and there's a load connected to those terminals. Yeah. And sometimes this next bit is a little bit tricky for you guys to get. Okay, but we can say that A is equal to N1 over N2, which we already said, also equal to E1 over E2, is also equal to I2 over I1. It's equal to any of the ratios in the ideal transformer equation. Yeah. All right.
Yeah.
So what we're going to do now is say that the generator sees, what the generator sees is an impedance, I should say Z dash there. Just cover that, Z dash, right? Generator sees impedance. Z dash between terminals. Such that reflected impedance Z dash is equal to E1 over I1. What we're saying there is, if we imagined that impedance was connected with that over here on this side of the transformer was taken away, connected as is here, we'd see an impedance that is equal to the voltage at the terminals, the voltage across the impedance, divided by the current. Yeah? You all understand that? This circuit here. If I gave you that circuit and said, give you the current, give you the voltage, you calculate the impedance Z dash as being E1 over I1. Yeah? Okay? Yeah or not?
Yeah.
Yeah, it's fine.
No. I'm starting to run out of, that's the only trouble with this, is I run out of space on the page quickly. You know, I can't extend the page like I can when I'm on the boards at work. All right? On the other hand, the secondary let's make the point a little thinner. Secondary terminals C an impedance Z is equal to E2 over I2. So if I said to you, going back to the diagram on my previous page, if I give you E2 and I2, you could calculate me the value of Z. Yeah, agreed?
Hang on, so those dash, like Z dash, is what the primary terminals see. On the secondary side, you call that just Z, but just with no dash. Is that what you're saying?
Yeah.
So, okay.
Yes. So you're connected at an impedance of Z. Yeah.
Yeah.
And when because of the application of the transformer ratio, the generator thinks it's got an impedance of Z dash connected.
Okay.
Now, if the ratio was A was 1, then those two would be of equal value. But
Okay.
because when it isn't, they're not of equal value. Okay.
Okay.
Yeah. So let's move on. So what we said is, if you were given, so what I've summed up here, what I've said is, if you're given the primary voltage and the primary current, you could calculate the impedance that the generator sees, Z dash. Yeah.
Yep.
And if I gave you the secondary voltage and the secondary current, you could calculate me the impedance connected. Yeah. Okay. So what we can do now is say Z dash, we've already said this, is equal to E1 over I1. Yeah. And from our formulae on the previous pages back here, we said that E1 can be said as equal to A times E2. So I'm going to substitute for E1, I'm going to write A times E2. Yep. And then also on that page, we said I1 is equal to I2 over A. So we're going to write I2 over A. Yeah. All right with that? And then we're going to take this, we've effectively got a fraction, because we on the top here, we could have A E2 over 1, we could write as, we got I2 over A on the bottom. So to simplify this, we do A times E2 over 1 times A over I2. Turn the bottom fraction upside down and multiply. Everybody remember that?
Yep.
Yeah. So we've got A times A is A squared. Yeah. Times E2 over I2. And what have we said E2 over I2 is equal to? on this page?
Z.
Z.
Z, yeah. So we can then, that means, so that's equal to A squared times Z. So we sum up, we can say Z dash, the impedance seen by the generator, is equal to the ratio squared times the actual impedance connected. All that for that. Yeah. I'm definitely not expecting you to be able to derive that like we just have. What I'm expecting you to be able to do is to use this formula down the bottom of the page here to calculate the reflected impedance. All right?
Mm-hmm.
Yep.
Yeah. So from that, what we can also do, we can sum that up a little bit further. I'll do it on another page. We've got secondary side. On one side, primary reflected on the other. Yeah. So we have secondary side Z is equal to A squared times Z. We call that Z dash. Yeah. The voltage on the secondary side transferred to the primary is I times E. We call that E dash. Yeah. And a current in the secondary, we can transfer reflect to the primary side as I divided by A. We call that I dash. All right. And of course, we can rearrange these formulae if we want to transfer back from the primary side to the secondary side just by rearranging them. All right. Any questions? And that will become a lot clearer when we do some problems. All right.
Mm-hmm.
Lewis?
Yeah.
Ben? Double Dutch?
Yeah.
Yeah. Okay, yeah.
Yep.
Warren?
Yep.
Yeah. And Robbie?
Yep.
Good.
Good.
All good. Right. Let's have a look at an example. I think we've probably only got 4 minutes left. Oh no, this is only a short one. Should get this one in. Right. 50 ohm resistor is connected to the secondary of a transformer with a turns ratio of 1 to 25. Yeah. So I is equal to 1 over 25. Z is 50 ohms. Calculate the impedance seen by the source connected to the primary. So this is what we've got. We've got a transformer here with a load connected this side that is 50 ohms. And the question's asking, what impedance does the generator see? So we simply use this. We've got to find Z dash, in other words. It's A squared times Z. Yeah. So it is 1/25 squared times 50 equals
0.08.
0.08 ohms. Yeah.
Yeah. Just
I mean,
thinking about that.
That's one turn on the primary to 25 on the secondary, so that's a step-up transformer.
Yeah.
Yeah, so a step-up transformer will reduce the impedance seen by the generator, i.e. more current will flow in the primary than the secondary. Yeah?
Yep.
All right?
Yeah. Just thinking, that little dash thing on the Z, is that called prime? I think I've had that called prime before.
In other topics, yeah, I'm not known it to be called prime. That certainly weren't called that in the textbook that I looked at when I put all this together.
Okay. Right.
But yeah, it could be. You're talking about the impedance on the primary, so someone might have used that terminology, but I haven't heard it used.
Yeah. Okay.
Yeah.
Yep.
I should just be calling it Z dash.
Okay.
Yeah. Because eventually we'll be transferring more than one impedance in the voltage from secondary side to primary side when we do our analysis on our model. So you need to get comfortable with this. All right.
Okay.
Yeah.
Mm-hmm.
Okay, we're 39.5 minutes, so I'm going to start a new meeting up. Okay.
Okay.